Hi class. Today we're going to talk about change of basis. So where we left off last time was talking about representing a vector in a certain basis, whether that was the standard basis or just some random basis that we decided to represent our vectors under. So remember that a basis is basically a representation of your coordinate system, right? So our standard basis, I, J, and K, is R2 and R3 as we're used to. So basically what we're doing is we're kind of manipulating what our axes look like. Maybe they're formed at an angle or something like that. Okay. So we're going to talk about today is not just representing a vector in a certain basis, but going from our vector representation in one basis to a completely different basis. Okay. So the first thing that we're going to go over is we have a theorem. So let's say that we have a basis that is represented by vectors. So my basis consists of n vectors, and each of those vectors has n elements in it. Okay. So let's say from that basis we make a matrix where that matrix is consistent of vectors from my basis. Right, so my matrix just looks like my vectors as column vectors. Okay, and let's say that we have some random vector that's also in Rn. Okay, so again, we have these column vectors that make up my matrix, and they form a basis. So that means that they are linearly independent, right? And they span Rn. I can make any vector in Rn out of a combination of these vectors. So I take those column vectors and I turn them into a matrix. Okay, take a random vector that also has n elements. Then if I want to represent x, my representation of x is that matrix times the representation of x in that basis. Right, so this is x under the basis b. So this x right here would be x in the standard basis. Right, so the standard representation of x is that basis matrix basically times the representation of x in that basis. Right, same thing here. If I want to go from the standard basis back into my representation of x in b, right, so the way that I view that vector x in the basis that I want, I take that that matrix formed from the column vectors, and I invert it and I multiply it times my representation of x in the standard basis. Right, so that's how we go from one basis to the standard basis, or from the standard basis to a basis of my choosing. Okay, so let's start with an example. Okay, so before we left off for our break that we're on, kind of a break, I gave you guys this basis, right? So pretty much the last example that you should have in your notes is a basis of these two column vectors, right? 1, 1 and 0, 1, okay? And then we had a representation of x inside of this basis, right? It was negative 4, 5. So I said, hey, let's look at this vector we have. It's the representation of this vector in this basis, okay? And what we wanted was, we wanted to know what x looked like normally. What does it look like under the standard basis? What does it look like in I and J, right? In this case, 1, 0 and 0, 1. The basis that we're used to. So basically a normal x-axis and a normal y-axis. What would be the regular way for me to look at this vector? Okay, and we found that out. We found out what x looked like. We did some math. So what we're going to do today is we're going to simplify that. Okay. So from this example, what I would do is I would take this u vector here, right? So this is my basis right here. And I'm going to look at u, which is the representation of this basis as a matrix. So I'm going to take my basis and I'm going to represent it as a matrix, right? 1, 1, 1, 1, 0, 1, 0, 1. So I basically just take it kind of looks like a matrix already, so I just form it as a matrix, right? That's what I'm going to use. Okay. So x is going to be u x of b, right? So I'm going to take this u vector and I'm going to multiply it times my representation of x in the basis b. This is the this is the x and b, and this is my u. So I'm really just going to multiply those two together, okay, in this order, u and then x and basis b. So multiply these together, and I get negative 1/4. So what we did last time was we wrote this out as a linear combination. So we're going to kind of expedite that process by looking at it as a matrix times a vector, right? So that's a lot easier than writing it as a linear combination, which is what we should have in our notes from last time. Okay. So let's say we want to verify part B of my theorem. Okay. So again, I just showed part A. Okay. I basically looked at what x looks like in terms of the standard basis, right? So now we're going to say we already know what x and b looks like, but we're going to go backwards, right? So we're going to take this U matrix, we're going to find the inverse, and we're going to multiply it times my representation in the standard basis, okay? So to verify part B, we're just going to kind of go backwards from what we just did, right? We're just kind of checking that it works both ways. So this representation in basis B is U inverse times x, which is what we had here, right? X in basis B is U inverse times x. So you can find U inverse on your own. We have lots of methods of doing that now. It is a 2x2 matrix, so you just find 1 over the determinant and then swap your things accordingly and multiply it out, right? So you guys should know how to find the inverses very quickly, especially for 2x2. So maybe verify that on the side as you're watching this video, right? So we have U inverse. I'm going to multiply that by my vector x, okay? And that's going to give me out negative 4, 5, which if we go back a few slides, that is what my representation was in basis B, okay? So, in general, from any basis to another, we have the following theorem, okay? So instead of going from one basis to a standard basis or back and forth, let's say I have two completely different bases, a basis 1 and a basis 2. If I want to be able to go back and forth between these two bases, I can do that in a couple of ways. I can go from basis 1 into the standard basis, and then the standard basis into basis 2, or it would be a lot nicer for me to go from basis 1 straight into basis 2. Okay, so say that B1 is a basis, B2 is also a basis. So B1 is the U's, B2 is the V's, right? So these are in Rn, so that's n vectors with n elements each. So that means U and V are both going to be n by n matrices, which is what we need. Okay, so let's say that U as a matrix looks like this. Each U is a column vector, and V is the column vector out of the vectors that form the basis here. Okay, and then again, let's say we have some random x in Rn. We can think of this as x being the standard basis, right? It's just regular vector in our standard Rn. Okay, so if I want to look at what x looks like under B2, okay, the V stuff, my formula is V inverse, right? This matrix inverse times the matrix U times my vector in the B1 representation. So what I'm doing is I'm going from B1 into B2. I'm already in B1, and then I'm going to multiply these by my vectors in a way that I end up with my vector in the B2 representation. So this first one is going from B1 to B2. Okay. If I want to go the other way, from B2 to B1, so if you notice, I already have it in B2, and what I'm looking for is B1. What does it look like in B1? It looks like this. So I already have it in B2. I'm going into B1. Okay. So here, if you notice, it's very, very similar. I take the vector representation I have already, and instead of V inverse U, it's U inverse V, right? So the order just kind of switches here between the placement and which one is inverses or not. So let's go through a proof of this. Okay. So again, the way the proofs work is we assume that we have what's already been given to us. So I know I have two bases and I have a vector, right? So say you have B1, B2, which are bases, and you can define U and V out of those bases. Then for every x in here, we have this, right? So when I what I'm doing is I'm saying I have these things and I want to show A and B are true. Okay, so I have my two bases and I have my vector. So the next thing that I want to do is I want to define what my matrices U and V are, because I'm going to need those, right? So before I can form U and V, I need to have the bases that those vectors, that those matrices are made out of. Okay, so U is the matrix whose column vectors are made from bases 1, and V is the matrix whose column vectors are made from the vectors of bases 2. Okay, so I know that X is the same as V times the representation in B2, and U is X times the representation in B1. Okay, I'm going to go back a little bit. Actually, we don't have to go back. We can look at that right here. Right? We have this from the first formula that we just did, the first theorem. Right? X in some basis is U inverse times that matrix. Okay, that's from going the other way. That's when I wanted the representation. When I wanted the actual vector, okay, X, it's that basis matrix times the representation in the basis that I'm already in. Okay, that's how I get into standard form. Okay, so my standard form is the matrix that makes up B2 times my representation in B2, or I can call it my representation in B1 times the matrix that makes up B1. Okay, so we saw that from before, right? So what I'm going to do is I'm going to play around with these two, with this equation here. So again, all of these are the same. If I did this, I would get out X. If I had the values and I plugged this in, I would also get out X. Okay, so just looking at these two parts, right, ignoring the X equals portion, if I multiply both sides of this equation by V inverse, I get V inverse V times my representation of B2, and V inverse U times my representation of B1. Okay, so V inverse times V goes away, right? And that will get me, I guess I'm missing some stuff. That basically will give me X of B2, right? Because V inverse V is I. So I'll have X B2, which equals V inverse U times B1. Okay, so this part turns into the identity, which leaves me with X B2. Okay, so I guess when I was writing this code, that part got skipped over. Okay, but this is I times X B2, which is just B2, right? Which equals V inverse U X B1. So if I wanted to show the other portion of this, the B portion, I would do the exact same thing. I would set up this equation, but instead of multiplying by V inverse on both sides, I would multiply U inverse on both sides, and I would get U inverse V B2. And I would have X in B1 left over. Okay, you could try this on your own. It's a very, very simple calculation to do. Again, it's just multiplying matrices either with left-hand multiplication or right-hand multiplication. Remember, your identity is like multiplying a matrix times 1. Okay, so this matrix V inverse U, okay, V inverse U right here, is called the transition matrix from P, the transition matrix P from B1 to B2. We call this P from B1 to B2. So I'm in B1 and I'm going to B2. So let's look at this one more time. I'll go backwards. From B1 to B2, I multiply my vector times V inverse U. Okay. To go from B1 into B2, I multiply by V inverse U times the vector that I have, right? So I'm in B1 going to B2. V inverse U is that transition matrix I'm going to use. Okay. Same thing for the other matrix. U inverse V is the transition matrix P from B2 to B1, right? So I'm going from B2 to B1. So the arrows indicate which direction you're going. You're already in this one. You're going to this one. P is the transition matrix or the change of basis matrix, right? So notice that B2 going to B1 is U inverse V, right, which is stated here. And that's the same thing as if I took this original matrix and just took the inverse of it. Okay, so that means that going from basis 2 into basis 1 is the same thing as taking that transition matrix from B1 to B2 and inverting it. Okay, they're inverses of each other. So these two things are related. Once you know one, you can find the other one very, very easily by inverting the one that you have, right? Either that, or you can completely calculate the new one by taking another inverse and doing extra matrix multiplications, right? So since they're inverses of each other, that means that the transition matrix from B1 to B2 is the inverse of the transition matrix from B2 to B1, right? So again, we also call this the change of basis because I'm going from one basis to another, right? So these formulas are very, very important, okay? B2 to B1 is this formula, and if I want to find the other one, I would take the inverse, or vice versa, okay? Whichever basis I'm going from to, right? So let's look at this. I know this looks kind of complicated, but let's think about this, okay? If I am in X, right, this is the standard basis. This is basis 1. This is the representation of X in basis 1. This is basis 2. And this is the representation of X in basis 2. Okay? So if I'm X and I want to go into basis 2, I multiply X times B inverse. And that's how we get into basis 2. So remember, when you're multiplying, if this shows up first, then that means that it is on the right side of the multiplication. I take this and I multiply it by that. That means this is first, and this multiplies on the left side, right? So when you're reading multiplication of matrices and vectors, it reads from right to left, okay? And we've seen that a little bit, like AX equals B. The X is being multiplied times the A. So if X is first, it multiplies times your matrix, with your matrix being on the left. Okay, I know in algebra we're used to thinking of it as we see it, X times V inverse, but it shows up the opposite way. V inverse times X will get you into your representation of B2. And I'm going to go backwards real quick just to verify that. So V inverse times X is your B2 representation, right? So if we go backwards a little bit, okay, right? So if I'm in X and I multiply by the inverse transition matrix, that's how I get my matrix in that basis, right? So remember, your X shows up on the right, and then your matrix shows up on your left, okay? So that's X times U inverse. It goes this way when you read, from right to left. Okay, let's come back. Right. So to go from X into B, the B2 version, you multiply these two together, but again, your vector is on the right side, V inverse is on the left. Okay. If I want to go from B2 into X, I multiply V times X, right? So V again is on the left, X is on the right. So if I want to go from B2 into B1, I can go into the standard basis and then multiply that result, which should be a vector, times U inverse. So U inverse on the left, that vector representation on the right, and then I can get into here. So if I want to go from B2 to B1, I can go into the standard basis and then from there change basis again. But what we just saw is a much easier way of doing that. Okay, if I'm in B2 and I want to go into B1, right? I'm in B2 and I want to go into B1. It's U inverse V. So I multiply my representation times V, right? So going this way, notice the order, V and then U inverse. V on the right, U inverse on the left. Remember, we read this way. So it would be this vector here. The next one is V, so V is in the middle. And the last one I'm using is U inverse, right? So reading it, it goes this way, but when we do the multiplication, it actually goes the other direction. U inverse times the V times the vector representation. But the reading goes this way. That's how we write it. Same thing this way. If I want to go from B1 into B2, I'm going to take my vector. It gets multiplied by U, and then that result gets multiplied by V inverse. Okay, so V inverse U, the representation of X in B1. So this map, as long as you know how to read it, is very, very useful. I definitely suggest that you put this on your notes for whenever the next exam is, which we'll have to talk about some other time, right? But this is a very, very good image. Just make sure you know how to read it and you're not trying to multiply xb1 on the wrong side, because first of all, you won't even be able to do the multiplication, right? So it works in that order. Okay, so let's do an example. Okay, so we got all of our formulas out the way. Hopefully you guys have been writing all of this down as we work through it, so you have a nice set of lecture notes to reference off of. So let's say that we have two bases. Okay, so we're going to go into R3 right now. So if this is a basis for R3 and this is a basis for R3, that means that these vectors are linearly independent, and since there's three of them, they span R3. Same thing here. This is another representation of R3. I can make all of R3 with these vectors. So both of these are R3. They're just being represented under different bases. So if I were to look at these as a set of coordinates or a set of axes, it would just not be my regular orthogonal perpendicular x, y, and z axis, right? It would be skewed in some way. So I have two different representations of R3, basically. So if I take a vector, I guess let's talk about what the u's will be. So u is b1, b2 is what I will call v, right? So my column vectors are here, right, in order. And these are my inverse matrices. So again, you can do these on your own, right? So at this point, I'm assuming you guys know how to find inverses. You can use your calculator to find the inverse matrix, right? Because again, doing it by hand can take a very long time. And we're getting to the point where we're using these things to do the math, right? The math is no longer finding these things, right? So we're using these objects now, so you need to be able to find them. So get used to finding them in your calculator, right? So just plug in your matrix, and then you basically say caret -1, and that should give you your inverse matrix, okay? So I have my u and my v for my basis, and I have my u inverse and v inverse also. Remember, I need all of these things in order to go from one basis to the next, so these should be the first things that I find. Okay, if I don't have these, it's going to be pointless to talk about going from one basis to the next at all. Okay, so my transition matrix from B1 to B2, if I want to go from here to here, it's V inverse U. So I take V inverse, I take U, I multiply them in that order. Okay, and this is my transition matrix. It's a lot easier to do this than to do it one at a time given any vector. So if I want to go from B1 to B2, I take any single matrix, any single vector, and I just multiply it times this matrix. So now that I have this transition matrix, I can use it to go from B1 to B2 for any vector I choose. Okay, so it's important to have this first. Now if I want to find the transition matrix from B2 to B1, I would just find the inverse of this matrix I just found. That's the easiest way to go from one transition matrix to the next. It's just find one, and then once you find one, find its inverse, and then you have the other. Okay. So again, that's what we're going to do here. So if I want to go from B2 to B1, I just use the matrix that I just found, because from B2 to B1 is the inverse of B1 to B2. Okay. So I just do that, right? So from B2 to B1 is the inverse of B1 to B2. So I take my transition matrix of B1 to B2, and I'm going to invert it. And now I have that transition. So if you notice here, I actually have both. If I take this inverse away, that's the first transition matrix from B1 to B2. And after I invert it, I now have the transition matrix from B2 to B1. So I actually have both representations here, right? If I disregard this negative sign, inverse sign. So let's look at some random vector. Let's say 1, 1, 1 in the standard basis, right? So nothing weird going on here. If I want to look at x in B1, I have to multiply it times U inverse, right? Remember, U is the matrix made out of basis vectors of B1. Okay, am I saying that right? U is the matrix made out of column vectors from the basis vectors of B1. So if I want to go from the standard basis into B1, if we go back and look at that chart, I have to go this way. Okay, so again, hopefully you have been writing these formulas so you can just reference them whenever you need to. Okay, so if I go to U inverse, which I found already here, okay, and I multiply it times my X vector in the standard basis, that'll bring me into B1. Okay, and so now that I'm in B1, if I want to go to B2, I can use my transition matrix, right? Use my transition matrix from B1 to B2, which is this thing, since now I have a representation in B1 of my standard basis vector. So if I want to represent myself in B2, I just multiply the representation in B1 times my transition matrix from B1 to B2. So when I put those down, it looks like this, right? So I take this matrix times this vector. Again, notice if I try to do it in the other direction, this one on this side, the dimensions don't match up and I can't even multiply them, right? So my representation of X under B2 looks like this. So then that brings us to our next theorem, right? So let S be a subspace of Rn with bases B1 that looks like this, right? K vectors, and B2 that also has K vectors. So these are K vectors, each with n elements. Okay, this should say of, not if. Define C as the matrix consisting of the column vectors of B1 under basis 2. Okay, so we're looking at these column vectors as they look under this basis representation. Okay, so we have K of those, and let's say we take some random X that's inside of this subspace. Then that representation under B2 is this matrix times the representation of X in B1, right? So what we're going to do, right, we're going to go through a small example. We're going to take a basis B1, we're going to take its column vectors, and we're going to represent its column vectors in the second basis that we have. We're going to turn that into a matrix, and then we're going to multiply our representation of our vector times that, in that first basis, times this C vector. Okay, so if S is equal to Rn, then this C matrix we have here is just a transition matrix. That's just our V inverse times U. It's our transition matrix from B1 into B2, because that's what's going on here, right? I'm taking my representation in B1, I'm multiplying it times some matrix that's all represented in B2, and I'm going to get out my vector representation in terms of B2, right? So this C should just be our transition matrix. So let's go through this as an example. Okay, so consider R2. So let B1 be two vectors, right, since we're in R2, and B2 be a different set of vectors that form a basis. So again, that means that these two vectors have to be linearly independent. These two also have to be linearly independent. That does not mean they have to be linearly independent from each other. Okay, in fact, they would not be, right? But these will span R2 and these will also span R2. That's what it means, again, to be a basis, right? So say that my representation of V1 under this basis, right? So the column vector, the first column vector for the basis in B2 under B1 is AB. And the second column vector under B1 looks like CD, right? So these are just very generic terms. Then what does it mean to have a representation under a basis? It means that V1 is A U1 plus B U2. So let's just go back real quick, right? A times the first basis vector and B times the second basis vector. So remember, your representation under a basis is just a linear combination of the respective elements, right? So A times the first column vector, B times the second column vector. So we'll do that for V2 also in B1. That should be C times the column vector V1 and D times the column vector V2. That's what it looks, oh, I'm sorry, U1 and U2. So C times U1 and D times U2 is what V2 will look like under B1 when we write it out as a combination. Okay. So the first element times the first column vector in the basis in B1, and the second element times the second column vector in the basis of B1. So that's how it looks in B1 because it's a linear combination of vectors from B1, right? So again, just to clarify, it's represented as multiple column vector, a linear combination of the column vectors of B1. That's why it's a representation under B1. Okay. So V2 will look like this under B1 as well. So let's take a random vector in R2. Again, this should just be in our standard basis. Then to look at that under basis 2, it will have a form x1, x2 of some form such that x looks like x1 times v1 plus x2 times v2, because again, v1 and v2 are the basis vectors for my second basis of R2, right? B2 is v1 and v2. Okay, so what this looks like in B2 is its components multiplied times the basis vectors, right? The first basis vector and second basis vector. So if we do a substitution for V1, okay, I get x1 times A U1 plus B U2. That's what V1 looks like, right? V2 also has this form in the basis 1, right? But we're just doing a substitution here, okay? So if I multiply these things out, right, x1 distributes across these components, x2 distributes across those two components, and we have this form, right? So what I'm doing here is I'm reorganizing x1 u1, x2 cu1, right? So I'm putting the u1s together and the u2s together so that on this next step I can factor them out. So x1a, x2c times u1, and here I factored out u2, so I have x1b plus x1d. So if I want to look at x in the representation of b1, right, so I had what it looks like in b2. So in b1 it has this form, x1a plus x2c, x1b plus x1d. Okay, and let's see here. So it looks like I made a mistake, and this should be x2. Okay, so again, that's what happens. So these should both be x1, and these should be both x2. So if you notice, this is now a column vector for x1 and a column vector of x2. So it's a completely separate basis, right? I have a write-up of this whole script, so I'll go back and I'll fix those errors before I post those. Okay. So again, right, this should be x2. That's an error from the write-up. I can pull that out times CD, and this x1 times AB. Okay. And if you remember, AB was our representation of V1 in B1, and CD is our representation of V2 in B1. Right? So if I pull those two things out, A, B, C, D, right, I have x1, x2. Okay, so I can write this as a matrix. So from a linear combination into a matrix equation, A times x equals some vector b, right? And we know x1, x2 is the representation of x under basis 2, right? That was that form. So now I have some matrix times my representation in B2 that gets me out my representation of x in B1. Okay. So if I call that matrix P for transition matrix, it is equal to the representation of V1 in B1 and V2 in B2, which if we go back quite a few screens is what I said, right? The representation of one basis, okay, in the terms of the other, right? So I'm looking at the column vectors of U1 in the basis of B2, okay? And that's what I did here. So I took the representation of this matrix in this form and I used that to form a transition matrix. Okay, so know that P is the transformation from B2 to B1. Okay, again, because I'm in B2 and I'm looking at what I look like in B1. Okay, and so I can rewrite it in this form since this is my transition matrix. So if I want to go from B2 into B1, I just take that P matrix times my vector. So it's really just what we've been doing before. We're just generalizing it further, right? So what does that look like? That looks like this matrix here, B1, B1, B2, B2, okay, and I have an extra parentheses here for some reason. I'll clean that up when I rewrite my write-up as well, okay, but this is just a matrix, so this should be gone. It should be this column vector and this column vector times forming a matrix times this vector representation of B2. And that is our lecture for change of basis. Okay, so if you go backwards to the example that we had where we were actually given two bases and a vector, and we're representing that vector in the different bases and finding this transition matrix, right? That's what most of your homework is going to be based on. Okay, so this example here that we went through at this time. Okay, given two bases, turning those into matrices, finding their inverse, and then finding your transition matrix. Okay, your two transition matrices, and then taking your standard basis and representing them in one form, in this case B1, and then bringing it into B2. That's really what this chapter, this section consists of. That is the problem you're going to be doing over and over again, right? So the rest of this lecture is really just to help you understand conceptually what these things are. I know the notation can be kind of thick, and I'm not there to explain to you in person. So make sure you guys use the discussion board that I'm going to post to ask any questions. I'll try to schedule a Zoom meeting. I can't get my camera to work, but I'll write all that in an email, or you should have already received that email by the time you get this. Okay, so I'm going to post one more video for this week, and then we will continue to post videos of this form in the upcoming weeks during our stay in place. Okay, have a good one.